haven't started yet. These handouts for you. Okay, so yeah, my name's actually going to start a timer just so I'll just look at the clock. Okay, so my name's Graham, and in this seminar I'm going to be talking about Kac-Moody Algebras, their classification, and a couple of their applications to physics. So my primary sources for this lecture are Chapter 7 of Fuchs and Schweiger, which to those of you in the symmetries class will be probably very familiar. And then also a set of notes from lectures given at the 5th International Mojave Summer School in Mathematical Physics in 2009. Those are by Professors Ella Jamson and Jacob Palmquist. So first, I'd like to make an overview of some relevant material from the Symmetries, Fields, and Particles course that was offered this term, of which the main point is that we care about Lie algebras. We care about the algebras because they can describe continuous symmetries. And the preface of Fuchs and Schweiger points out that having this kind of algebraic description in place is really the key step that allows us to take the huge body of algebraic tools out there and apply them to physical questions. The key algebraic tools that we're going to use here are not very abstract. They come from linear algebra, things like eigenvectors and determinants. But it's worth knowing that these emerge from a much richer zoology of abstract algebra techniques, which I can't speak for everyone, but I personally would like to learn a lot more about those in the near future. So yeah, let's begin. In symmetries, we showed that a finite dimensional simple Lie algebra, which has dimension D, can be identified up to isomorphism from its Cartan subalgebra H of dimension R and its root system D, which then has dimension D minus 1. Then we were able to construct a system of simple roots, which in fact is representative of the entire root system. And what we'll show is that this can be represented by a basis also with dimension R, so there's a nice kind of parallel there. When we talk about roots, and these roots are values in phi, but they're also members of the dual vector space Q Cartan subalgebra. And we can visualize this kind of just as projecting it onto the blackboard as a space. We looked at pairs of roots, and we showed that by dividing this dual space into a hyperplane and also identifying pairs of roots across the origin, we can divide this into sort of two sectors. And then we defined simple roots as all those roots such that they cannot be composed as a sum of two other roots within the same sector. So geometrically, this sort of just looks like whichever roots are kind of closest to the origin don't have any other roots closer that they can be composed from. From this, we proved some helpful results. For example, that for any simple root, its additive inverse must also be a simple root. And then that for any two simple roots, their difference cannot be simple. And continuing from there, we were ultimately able to conclude that these simple roots span the realification of the dual space, and that they form therefore a nice basis for that. Sort of putting that away temporarily for now, we also looked at the Cartan-Weil basis for the Lie algebra as a general form describing it, which allowed us to write down some commutation relations. So first we have Cartan generators, which form the maximal abelian subalgebra of the Lie algebra, and obviously are abelian. And then we also had some step generators, which relate in a nice way to the Cartan generators. And this connects very directly to the root system of the algebra. There are also relationships between the step generators which lead to other step generators if those exist. But really, this is the key point that shows us how the root system is connected to the Cartesian subalgebra. But now that we know about simple roots, we can form an even more concise description of the Lie algebra. And we can do that by using root strings to prove that any inner product between two different roots, can be normalized with respect to one of those roots, and you get something which is named. And this overall set of values is what we call the Cartan matrix. And then this Cartan matrix allows us to then take this description and write down, in some ways, a better one, a more concise one. That's called the Chevalier-Serre basis for the Lie algebra. So we, again, write down some generators which will look a lot like the Cartan generators, but are not the same. So they are abelian. And then we write down, again, some step-like generators, which relate to these by the Cartan matrix elements. From there, what we wanted to do is compute the commutators between these raising and longer operators within their own system. And this allows us to fill out the entire set of roots of the Lie algebra. For the sake of time, I'm not going to go through that whole derivation, but the result will ultimately be applicable to the general class of Kac-Moody Algebras. And the two main results are that commutators between a raising operator and a lowering operator, well, they're only non-zero if you're talking about the same index operator. And then what's known as the Serre relation, which states that when you take a series of composed add maps of one of these raising operators or lowering operators to another, you ultimately get to zero. A whole bunch of these, and then some potentially different one. And the number of these that is required for this to be zero, the number of these composed add maps is just 1 minus the Cartan matrix element for those two step generators. And again, this is called the Serre relation. And the statement that these strings of commutators ultimately close out shows that the Cartan matrix contains all the information about the root system and therefore the Lie algebra. However, the Cartan matrix, as described so far, can't just be any R by R matrix. It has to satisfy some certain characteristics, which I'm going to state, but not thoroughly derived. So the first is that all the diagonal elements have to be equal to 2. And the off-diagonal elements, if it's equal to 0, then that usually implies that the transposed element has to also be equal to 0. And then that any remaining off-diagonal elements are negative. Then we have two sort of more general scope requirements. The first being that the determinant of the Cartan matrix is greater than 0, that it's positive definite. And then that the Cartan matrix is irreducible. That is that it doesn't have, there's no rearrangement of roots such that you end up with a nice block diagonal form like this. That's not allowed. So the first two of these requirements are fairly fundamental to working with any symmetric scalar product, at least in the way that we chose to normalize, where you end up with some constant value on the diagonal. The third came from the existence of simple roots. So in a qualitative sense, that's just important for stating the well-orderedness of the root system. And the fifth is kind of just sensible, because if we have a separable system, it would make more sense to separate it rather than not. And we're not really losing any generality there. We're just saving ourselves some time. But the fourth requirement can, in fact, be loosened and even removed. And that's how, just by striking that out, we reach the more general realm of Kac-Moody algebras. So Kac-Moody algebras, weird spelling. They have several wide subdivisions, which will help us to provide some insight into what sort of objects they are. We're going to limit ourselves to symmetrizable Cartan matrices here. So these are matrices A such that there exists some diagonal matrix D where dA is symmetric. And this is a significant restriction, but it will turn out not to be a huge restriction. We'll still end up with a lot of nice diversity of algebras here. And to prove that this can be done, we can explicitly construct what this diagonal matrix looks like. That comes from recalling the definition of co-roots, which are these alpha caret. They're a normalized version of any particular root. And in many ways, this is just a semantic formula that lets us write down the definition of the Cartan matrix in a nicer way as an inner product between some root and some co-root. There is a deeper meaning to this, which comes from looking at the dual of the Cartan subalgebra, but that's not really important here. The main point is that these exist, and therefore we can take our highest root, called theta, and expand that into a linear combination of the simple roots. Then we can do the same thing for the co-roots, for the simple co-roots. And these coefficients that we end up with are respectively called the Coxeter labels of the root system, or the Lie algebra, and the dual Coxeter labels. So then these Coxeter labels actually do have a lot of other applications, but the key one we're going to just write down is that this diagonal matrix can be expressed as kind of a diagonalization of the vector, which is the element-wise ratio between roots and co-roots, simple roots and co-roots. So having done this, once the Cartan matrix is diagonalized, we can construct a partition of all the Kac-Moody algebras according to their matrix signature. So the first case is the one we already know about, where all of the diagonal elements are positive. And this is called the finite Kac-Moody algebras, which are totally equivalent to the finite semi-simple Lie algebras. We know that these can be classified in a nice way. That's the Cartan classification, which I've put up the diagrams over there. A slightly more interesting case is when there's one zero element on the diagonal. This is called affine Kac-Moody algebras. And as we'll show, these can also be completely classified in a way analogous to the finite semi-simple Lie algebras. Importantly, affine Kac-Moody algebras can also be defined without worrying about this diagonalization. So this is equivalent to saying that the Cartan matrix meets two requirements: the determinant being zero, and it having the property that if you take the Cartan matrix and sort of cross out any two matching, rows and columns around some root, that what you end up with is either a finite simple Lie algebra or a direct sum of them. It has to have a positive determinant once you've done that for any index. But there's more beyond this. So outside of these two, they're not so easily classifiable, and those are called indefinite Kac-Moody algebras. But they do still have some interesting physical applications. And the special case that has the most interest is when there's just one negative eigenvalue of that diagonal. These are called Lorentzian Kac-Moody algebras. And similarly, these can be defined, well, not quite defined, there's a subset of these called hyperbolic algebras, which have a very similar definition to this, where the determinant can now be less than 0, and when you cross off these rows and columns, you get something which is as a direct sum of either affine or finite Kac-Moody algebras. So it's just kind of the below this definition that we already gave. As a side note, this removing rows and columns is equivalent to just deleting some single vertex in the Dicke diagram. So that's a nice geometric way to think about that. So we'll look at the affine algebra case in some more detail because the restriction of having determinant 0 makes it not too hard to do some meaningful computations. So the rank R of an affine Cartesian matrix is just one less than its dimensionality that comes from the determinant being 0. So we can look at 2 by 2 matrices as the simplest possible case. We know that they have to have 2 on the diagonal, which just leaves us with 2 undetermined entries, which have to be negative integers. So it's not hard to see that there's really only 2 possible cases here. They could both be -2, or you can have one -4, one -1. Now, recalling the notation for the Dicke diagrams for the various infinite sets of finite dimensional Lie algebras, since we've already said that these affine algebras sort of contract to a finite algebra upon the removal of any vertex, and because those finite algebras we've already thoroughly classified them, it makes sense to just classify these affine algebras by the finite algebras that they contract to. So we can label these affine algebras accordingly. So A1 parentheses 1, A1 parentheses 2. And the A1 comes from, if I cross out any of these rows and columns, I end up with just a 1 by 1 matrix with 2 in it, which is the simplest case of the finite Lie algebras that we talked about. So before moving on to a higher dimensional example, we can prove diagrammatically a nice lemma about the allowable off-diagonal elements of affine Cartesian matrices. So from our definition of removing elements from the affine algebra and getting a finite algebra, direct sum of finite algebras, we can go further and say, let's start with some affine Cartesian matrix and just keep removing rows and columns. We can do that. And then we know that ultimately we'll end up with, if we remove enough of them, just some 2 by 2 matrix. And we can do this and we can get any square 2 by 2, well not square, but a rectangular set of 4 elements in the original matrix that we like. And that this final matrix we end up with, well, it must be one of the rank 2 finite dimensional Lie algebras. There's not very many of those. There's A1 direct product A1, there's A2, B2, and G2 is one of the exceptional cases. And by looking at the matrix elements of these, which are just, I'm not going to write them all down, but none of them none of the negative off-diagonal elements are lower than -3. We can get some general rules about what all of these elements must look like. So for the affine case, all the matrix elements must be within this discrete set of 0 to -3. Again, because this is the only case that has 0 in the off diagonals and they're both 0, we can say that just as we find semi-simple Lie algebras, if some off diagonal element is 0, its transposed element again must be 0. And then lastly, that the product of some off diagonal element with its transposed element must be less than or equal to 3. This just rules out the case of 2, 2, minus 2, minus 2, which we already showed is not a finite algebra, but an affine one. So with these rules in place, we can look at higher dimensional examples if we want to. For the sake of time, I'm not going to run through a higher dimensional case entirely, but one interesting one to look at is the set of three-dimensional affine algebras, affine Cartan matrices that contain the special Lie algebra G2. G2 has a matrix which looks like this. So in solving for these elements, you arrive at two different cases, which, well, one of them fills in -1, -1, 0, 0 here. And you can show that that determinant is 0, and one just flips each of those pairs. So those two cases, once again, we can label them like we did somewhere before by saying that because they both reduce to G2, we're going to call them G2-1 and G2-2. Except just to make things fun, we're not actually going to call this G2-2, we're going to call it G2-3. And there is a reason for this, which is not immediately obvious to me anyway, but it comes from studying how finite Lie algebras can be sort of upgraded to loop algebras, which is the space of possible continuous mappings of the circle S1 to some Lie algebra. And that space ultimately allows you to derive the set of affine algebras which come from that finite algebra. And the number of coverings of the circle which are used in that map is the label that you end up with here. So the 1 cases are just notationally called untwisted affine Kac-Moody algebras, and the 2 and 3 cases are called twisted. That's sort of a side note. So the procedure here can be extended to for any size of Cartan matrix, and it leads to an extended set of Dickin diagrams which totally classify affine Kac-Moody algebras. On the handouts, I have drawn, I think, all of those, hopefully all of those. I'm just going to point out a couple interesting examples up here, because diagrammatically they all correspond to just adding a node somewhere. There's one pretty interesting one which is derived from the A case, where you have a string of roots going across, and then topologically it actually comes back and is circular. That's an allowable affine algebra. Many of the BCD cases just come from adding a node on one end or the other. And then some of these exceptional cases, actually all the exceptional cases, give 1 or 2 more exceptional cases. So for example, E6 goes to an E6-1, where that sort of split off node in the middle gets another one added onto it. So in this way, there's a full classification, and we've shown that kind of using the same procedure with the Chevalier basis that was used for the finite algebras, we can go back, we can take any of these diagrams, any of these Cartan matrices, and arrive back at a symmetry group. So the last example that I want to go through, and this will just help lead us into some physical applications, as to derive the root set for the A1 case that we talked about before. So this case has a Cartan matrix simple roots, which without losing any generality, we can just call them delta minus alpha and alpha. And it's going to be useful to represent these on the grid of alpha and delta. So this root is over here. This one's here. Using the, oh, it's good, it's still there. The Say relation, which we derived before, we can look at combinations of the step generators that correspond to each of these roots, and we can find some more roots that we know must exist. So for example, we can take, define the step generators that correspond to each of these as E0 and E1. We could take a commutator between those two, and because there's not enough add maps here to arrive at the end of the root string, we know that this must be another root. This does not equal 0. And just adding these two together vector-wise gets you a root here. You can do this again and get another root here. But if you try to do it a third time, now you have 3 E0 maps on top of the E1, and because AJI for the off diagonals is -2 here, it's exactly 3 that are enough to get you to the end of the root string. So this is not allowed. Similarly, if you go in the other direction and try to add, for example, E0s to the E2, you can get one more because that's just the map. E0, E0, E1, that's fine. But if you try to add another E0 to that, again, now with the labels reversed, you're getting to the end of this Say relation. So that is not a root. And you can continue this recursively and prove, that essentially you can prove that there's a railroad tracks of roots going infinitely in both directions here, with the only exception being that this one is also not a root at the origin. Writing down that root set formally, just for fun, is some number of the delta elements plus or minus alpha. That's for all integers. Union delta for all integers except 0. This describes that full set of roots, and clearly this is countably infinite. This is not a case which ever shows up in any of the finite semi-simple Lie algebras because they're finite dimensional. But since this is the simplest case, it's believable that for all affine Cartesian matrices, more complicated than this, you will always get an infinite root set, and therefore an infinite dimensional algebra, which can then be exponentiated to give an infinite dimensional symmetry group. So I'll wrap up just by briefly talking about a few of the applications of Kac-Moody algebras. So these affine algebras, which we went through in some detail, have a direct link to Virasoro algebras, which are also infinite dimensional, and they generate the infinite group of conformal symmetries, which come up in 2-dimensional conformal field theories. Virasoro algebras are also deeply involved in string theory, where you can have a world sheet which maps out the position of the string at all points over time. And you can write this in a mode expansion. This is a solution to the wave equation of motion for the string. And these modes that you end up with, when you quantize the string, you can form combinations of these, which follow this so-called Virasoro algebra system. So the symmetries that come from a Kac-Moody algebra ultimately end up being the symmetries of the string. For more on this, there's a really nice set of lecture notes from a course that was taught here years ago. This is the archive number for math representation theory. That's 2. On the other hand, the hyperbolic case of Kac-Moody algebras, which we said is not as well understood, they can come into play in the dimensional reduction of gravity and supergravity theories. This is because the single negative eigenvalue in the signature of those algebras gives rise to the conformal scaling symmetry of the metric in those theories. For more on that, there's a really nice, interesting paper which I haven't read past the first couple pages of. No, it's not that theory. So that's all I have. Yeah. Are there any questions?
Okay, let's give Graham a round of applause. Any questions?
So how does the how much the representation theory for Kac-Moody algebra, like the theory of highest weights, for instance, for finite dimensional semi-simple algebras, gives some sort of nice tools to understand representation.
Sure.
Do you know whether there's anything you can do with Kac-Moody algebras in that vein, or?
There definitely is. I don't think I know the details of it, but I've seen further chapters in some of these papers that look like there are. Yeah.
So in symmetries, once you deal with this Cartan stuff, you end up with identifying these the algebras on the left here as the algebras of familiar groups like SU n+1 and SO2n+1. For some of the maybe smaller Dinkin diagrams for the affine section there, do you know of any groups that these correspond to once you exponentiate?
I did see some mention of those groups. I didn't find that they were labeled in any kind of memorable way as the SU and SO ones are. I think maybe just because there's so many of them.
Sure.
And in the literature, just for one example, the three-dimensional case that I was going to go through has like 5 different labels in different papers in the literature.
Right, okay.
Everybody has their own notation.
Sure.
So, yeah. Yes.
You know, the Kac-Moody algebras correspond to two spaces of the groups. Do the Kac-Moody can correspond to some sort of groups?
The group that you end up with is some kind of infinite dimensional symmetry group. I think the form that takes is not obvious to me.
So they're infinite dimensional manifolds?
I think probably it's possible to describe them that way. And it's tricky because we're not really starting with a physical thing and going to an abstract description. We're starting with this more general abstract description, and then we kind of have to figure out what different physical things it could be applied to. But I'm sure there's some examples of that.
All right, let's thank the speaker once more. And the next talk will be in 5 minutes.